Hi everyone, my name is Zhuowei Wang. Please allow me to introduce my work, SemiNLL, a framework of noisy label learning by semi-supervised learning. It has been accepted by transactions on machine learning research.
The first section is the introduction. Let me begin this section by asking two questions. What is label noise, and where does it come from? Noisy labels are common in deep learning communities. For example, some images are really hard to distinguish even for human eyes. In this CIFAR10 dataset, this cat and this dog can be easily mislabeled by human annotators. Also, when we use search engines or download social media images, they might yield a certain number of wrong labels in the dataset. This is a real-world dataset called Closing1M, in which there are 1 million closing images crawled online. The noise ratio is approximately 40%. Deep neural network will easily get confused when 40% of the labels are wrong. Since we don't have a prior knowledge about whether the labels is correct or wrong, we can't make the right decision for classification. Here comes another question. How does noisy labels affect deep neural networks? The answer is so obvious. When deep neural networks are trained in a dataset with noisy labels, their predictions tend to fluctuate and vibrate, showing a sense of instability. Another important thing of deep neural networks is that they tend to fit to clean labels first, and then overfit to noisy labels. In this case, the wrong information they learned from those noisy labels lead to poor robustness and generalization performance. As you can see in this graph, even in a small and simple dataset like MNIST, the higher the portions of noisy labels, the worse accuracy you can get for DNA. Since noisy label is an important question in deep learning community, how do previous studies tackle these noisy labels? And what challenges are they facing? The first kind of method is called noisy estimation matrix. These works use some heuristic methods or even clean samples to construct a noisy transaction matrix, TX, to correct model prediction of DNN. They use this matrix to multiply the original prediction of the model in order to get a relatively accurate result. In a way, they fix the prediction of the original prediction of deep neural networks. However, the challenge for this method is that TX is sometimes really difficult to estimate, especially in datasets with many classes. Another kind of the method is called sample reweight. As I mentioned before, DNNs tend to fit clean labels first and then noisy labels. Thus, clean labels fitted first have smaller losses than noisy labels. In this way, some researchers use meta-learning and curriculum learning to assign a weight to each sample's loss calculated from the model in order to reduce the effect of noisy samples. However, no matter how small the weight you assign to them, the effects of noisy labels still exist and will further degenerate the performance of different networks. So, the sample selection is the way that eliminates the effect of noisy samples completely. They only select those labels with small losses to train the model because they regard those samples as clean ones, and they discard samples with large losses. However, useful image information might be discarded together without further exploiting. This sounds a little bit pity, especially when the noise ratio is high. Then most of the samples will be discarded, so there aren't there aren't many samples left to do the training. This will lead to my research problem. How do we leverage only the image content of noisy labels, instead of discarding them completely or letting them destroy the training process of my neural networks? I will explore deeper in the second section, preliminaries. One easy way that I can think of is to conduct sample selection first, which is to divide the clean sample and noisy samples into two different sets. And we will regard the clean samples as the labeled set in semi-supervised learning setting, and we will discard only the label of the noisy samples and regard them as the unlabeled set in the semi-supervised learning setting. And in this way, we can transfer our noisy label problem into a semi-supervised learning setup. As you can see in this graph, first of all, we use GMM to distinguish clean and noisy samples. And after that, we will feed XE and UE into the semi-supervised learning backbones mix match, and I will introduce them later. Let me introduce one sample selection strategy called GNM. It is short for Gaussian mixture model. It is an unsupervised clustering method that we use to distinguish clean and noisy samples. This graph here shows the normal distribution of the loss of clean samples and noisy samples. And we can see clearly that there are two different clusters. So what we need to do is to fit each sample's loss into the GNM to figure out which clusters each samples belongs to. And then we can get the probability of each samples being clean. Based on the probability threshold, Wi, we can divide the whole data set into the labeled set and the unlabeled set. After the sample selection phase, we use mix match as our semi-supervised learning backbone. Basically, it uses mix up to mix images and labels to form new input and target. And then it calculates cross-entropy loss on labeled samples and mean square errors on unlabeled samples. But why do we just stick to GMM and mix match? I mean, there are many sample selection methods, and the semi-supervised learning community is growing very fast. So my motivation becomes to find out if there are meta and once-for-all and versatile framework that can utilize the power of any sample selection methods and semi-supervised learning backbones. So we propose a plug-in and use framework that divides the whole dataset into clean and noisy set. The problem is then transferred to a semi-supervised learning setting, which use the labeled set to guide the learning process of the unlabeled set. Here's the pseudocode for our algorithm, which is called SemiNLL. It is a framework that can utilize the power of any sample selection methods and the semi-supervised learning backbones. To do that, you just need to replace the placeholder select and the semi with specific sample selection methods and semi-supervised learning backbones. And we also propose a new sample selection method called self-prediction divider. Based on the fact that DNN's prediction tends to be consistent on clean samples and inconstant on noisy samples, SPD selects the correct samples by the agreement between the original labels and the model's own predictions. As for the semi-supervised learning phrase, we use these two methods as our semi-supervised learning backbones. And these are all the instantiations of our framework. And And as you can see, you can combine all the methods you know based on our framework. So there are many more possibilities and combinations that you can try. This part is about experiments. And the first evaluation metric is the accuracy. And we've conducted thousands of experiments to show the effectiveness of our framework. And we pick this table, and you can see here the instantiations of our framework, GPL and divided mix plus, achieved the best test accuracy across 4 datasets. The benefits of using SSL methods in our framework can improve sample selection performance incrementally. As you can see here, the label prediction ability of divided mix plus and GPL are much better than divided mix and divided mix minus. Another benefit of using SSL methods is to leverage the potentially noisy samples to learn a feature representation, which is represented by the SNE graph here. Both GPL and divided mix plus can accurately separate the clean instance of 2 classes. The SSL backbones of GPL is more effective in isolating noisy samples from clean ones.
Here's the training time of all the instantiations of our framework. As we can see, divided mix plus is much faster than divided mix, showing that the instantiations from our framework work more efficiently than simply combining SS and SSL components. And are there any rules of this framework, and are there more synergy combinations from our framework? So in order to answer that, we conducted a holistic comparison of all the instantiations on CIFAR 10, and here's our conclusion. As for the rules for sample selection, we found that for symmetric noise, GNN is better than SPD and vice versa. As for the rules for SSL, we conclude that we need to choose the right SSL for different noise types and noisy ratios. And we found a most synergy pair, which is GNN plus pseudo labeling, because it achieves the best result among all the noise ratios and noise types. And that's the end of the presentation. Thank you for your time.